Hello, I'm Mike Ehler, author of the $50 and Up Underground House book. We're going to present 3 tapes for you, sold in 2 tape packages and probably a 3 tape package also. The first tape is going to take you through the basics of underground construction with the post-shoring polyethylene method. And we'll be seeing some slides of structures that we've built ourselves, myself and volunteers and some paid professionals. The second tape will take you through a design course of the 13 approved methods of underground design, radically different than the 4 methods used by most architects today, and we think radically better. And in that second tape, we'll also be doing a actual hands-on session with materials that come in the low-cost underground house workshop booklet that we give you here with the course. You'll actually be designing in underground structures in this course, in the second tape. And hopefully, if we have time in that tape, we'll go out in the field and we'll see some of my underground structures. The third tape in this series deals with shelter exclusively and also with earth-sheltered greenhouses. Many of you may be worried about the times ahead, and we're going to teach you how to build a structure ranging in cost from $50 to $500 that should take you through anything with the exception of flood. That is to say, it'll take you through fallout, it'll take you through high winds, probably up to 200-300 mile an hour winds. It'll take you through most earthquakes and heavy-duty fire, forest fire, range fire, whatever sort of fire may be coming. It'll take you through probably anything except flood. That's the third tape. I've been living in an underground house myself since 1971, and it's a house that I built for $50. And I'm still living in part of it, or I'm still living in it, and I've added on to it. I've turned an original $500 or $50 underground house into a palatial $500 underground house. And we'll be seeing some slides of that, and again, hopefully we'll get out on the site and see the house itself. Totally pleased with the house. Been there since 1971. The place is holding up very nicely. Even the $50 underground house, I did have to do some modification on it because I didn't treat my posts, and we'll be talking about that later. So I did have to do a little rebuilding on it, but parts of it are exactly as it was when I first put it down. For example, the roof. And I have almost no leaks in there. Once in a while, during spring breakup, I'll have a little leak in that house for a week or 2. But the rest of the time, no matter what the rains are, I don't have any leaks in there, either from the walls, from the floor, or from the roof. The place, the original $50 underground house, is, I sort of compare it to Henry Ford's original Model T Ford. And I don't think Henry Ford's original Model T was still on the highway after 21 years. But this original experimental $50 underground house is still serving me well. It's where I do my cooking, and it's where I sleep. It's where part of my library is. So 21 years of experience gives me the confidence to be able to tell you that if you follow closely what we are going to teach you today and what we teach you in the book, the $50 and Up Underground House book, which is a companion to this course, if you follow these instructions closely, you should come up with a very livable house for a fraction of the cost of building the normal frame housing that's That's the norm in America today. There will be a number of questions that you'll have. Fortunately, I've given this course to audiences of all size, ranging from single people to 250 people at a time. And there are a great many questions that come up. We're doing this in a studio today because the last time we tried to tape in with a live audience, it didn't come out well. So we're trying with a studio shot today. We won't have the live feedback that we have with the live audience, and I won't have those questions coming up to me like we usually have. But hopefully I'll remember the questions that were thrown at me during the other occasions, and I'll be able to answer those questions as we go along. I'm not real fond of what's being built in America today. We're not building things sturdily. We're building structures with poisonous materials, poisonous building materials. We're building structures which are environmental disasters, and we can do much better. I haven't had any funding from any foundations or anything, so the places we'll be seeing today are going to be simple structures. I think the most expensive structure we'll see today cost $8,000. So our range in building costs range from $50 to $8,000, what we're going to show you today. Much of the cost cutting is due to the fact that most of the people who follow these methods do much of the work themselves. The $8,000 underground house is the one that had the most professional help on it, and that was about half built with professional help and half with the owner-builder himself. We'll see houses that were built almost entirely by the owner-builder. We'll see one that cost $2,000, which made the cover of Earth Shelter Living magazine. And we'll see another one that cost, I think, $4,000, which was partially built also with professional help. One of the ways that we cut our costs is by salvaging materials. The other way that we cut our costs is by building with earth. Earth is a large component of our structures, and they are actually part of the component of the structures. The earth is a structural component, as we'll see here shortly. We build with a system called post-shoring polyethylene method, or PSP. And let's zero in here on a comparison of the post-shoring polyethylene method, which is to sink a post into the ground, and originally we were treating the post with a poison treatment. We no longer use the poison. We'll be explaining what we're using instead, what we are using instead. Behind the posts, between the post and the earth, is shoring. And living as I do up in a logging area, I was able to get a lot of materials that the sawmills threw away, and that's what went into my original $50 underground house. And much went into other structures that I built. These are called mill ends. They're thrown away by the mills. If you have to buy lumber, you can buy oftentimes a poorer grade of lumber and use that in these structures, with the exception of the roof, and still get away with cutting your building costs drastically, because if you can use the timbers off your land, assuming that most of my people build on their own pieces of property, if you can get the timbers for the posts girders and beams off your land, then all you have is the cost of the shoring that goes behind that, the lumber that goes behind that, and the polyethylene that goes between the lumber and the earth, which makes the moisture barrier. You also will have flooring, which, in my case, and type of flooring that I push very hard to get people to accept, is what I call the earth carpet floor. And that's to lay down that's to smooth the floor very, very carefully, like a cement mason, get it that smooth. And then lay down a layer of polyethylene and then roll out a carpet on top of that. And it's like walking on a golf course green, and it just cuts your costs drastically and has a number of other advantages. But compare this method with this over here. Over here you've got expensive footings. You have to build shoring around the footings. You've got studs, insulation, sheetrock, fire stops, sheathing, building paper, siding, nails throughout. And you have to build 2 walls to pour the foundation. That's a lot of material, and that's a lot of manpower that goes into building that structure as compared to this. And there's also a lot of expertise that goes into that structure as compared to this. Almost anybody can build this structure. You may need some help around your work, the professional carpenter on your plumbing, perhaps, and a professional plumber on your plumbing, the carpenter on your carpentry, and perhaps an electrician. But those are minor costs compared to the costs of building this, compared to the labor involved in building this. So we're going to push very hard to convince you to go the post-shoring polyethylene method. If you, in particular, of course, if you're in a timbered area. If you're in the Southwest, you can get away, we think, with a structure that has adobe walls or rock walls. You're going to have some problem on those with lateral thrust. If you've got a, say it's on a flat land, and you make an excavation, and you put in a wall, and you backfill, you're going to have what we call lateral thrust. And with our post-shoring polyethylene method, as we'll explain in a while, the lateral thrust is automatically taken care of. It's counterbalanced by the thrust over here. But if you're going to build down in the Southwest and say, try to put in an adobe wall, and you backfill, it's going to want to push that adobe in. Now, there are 2 things that you can do in this case. I have to interject here and also say you're probably still going to need posts or concrete piers or something of the sort to support your roof, and the adobe would go in between. I don't think the adobe itself is strong enough to support a roof. You can ask an engineer on that. Certainly a rock wall would be enough. But you have a problem with the adobe, with this lateral thrust. Now, there are 2 ways of handling that. One is to leave what we call a vertical crawl space out here. Build the wall up here and not backfill out here. That takes the pressure off the wall. If you do want to backfill, there's another thing that you can use. Put the backfill in here and you've got the pressure. There's one other thing that you can use on both the rock wall or brick wall or cinder block, although I don't advocate using cinder block, or an adobe wall. And that's a product, I can't give you the brand name, your hardware store ought to be able to find this for you, but it's a plaster that has little fiberglass shreds through it. And the fiberglass acts as reinforcement. And people have been using these since it was invented. People have been using these on cinder block basements because oftentimes a cinder block basement wants to push in on you from the lateral thrust. And when they plaster it with this plaster with the little fiberglass shreds, that's strong enough. So what I'm saying here is down in the Southwest, in those areas where you don't have abundant timber supply, but you may have rock certainly have adobe that you can make, or Cinveram bricks. You can still build with this method. Before we get into the details of the post-shoring polyethylene building method, I do want to talk first about some of the reasons for going underground. If you look at page 1 of your workbook, see the first thing up is no foundation. Now that might not sound like a whole lot, but when you consider most frame houses, you'll know that you have to put those frame houses up on footings, foundations, the earth. Normally they go down about 3 foot or so beneath the earth's surface here, so that they don't have the thrust, the permafrost thrust, the thrust when the earth freezes and the water in the earth wants to bow up, and that cracks a lot of foundations and so forth. So they usually go down 3 foot below, and they usually go up 2 to 3 foot above, so that they have what they call a crawl space in here. And they put a wooden floor in here. The crawl space is in here so that you can crawl around underneath and work on your pipes, work on your electricity, check for termites, and so on and so forth. Unfortunately, what the crawl space does is it brings in cold air in the wintertime. You have to have some ventilation in there. Otherwise, there's a moisture buildup, and it begins to rot your wooden floor. So you have to have some ventilation in there, and you're bringing in the cold. So you have a cold floor. Plus, this is, to put in these footings, this foundation, is generally about 15% the cost of the house. Now, for that 15%, often we can build an entire post-shoring polyethylene underground house just for the cost of the footing. And it's better when you have an earth carpet floor. Earth carpet floor, you have no cold air coming in underneath. Your pipes are never going to freeze because they are down in the solid earth, which is about 6, 8 foot beneath the surface of the earth anyway, and then they're down a foot or 2 in solid earth underneath your floor. So your pipes never freeze. They freeze here. Your wooden floor is never going to rot because hopefully you're not putting down a wooden floor. You're not going to get termites in there. Again, because you don't have a wooden floor. You've got the earth carpet floor. And the cost of this flooring here is the cost of your carpeting, which you're going to put down generally, usually, on your wooden floor anyway. And the very small cost of the polyethylene. Polyethylene is the one artificial manufactured substance that we use throughout this construction, and we approve of it. As one of my old-time hippie friends said, polyethylene is an advance, and it is. It's useful. Its cost to the environment is minuscule compared to most building materials, and it's benign. That is to say, it doesn't outgas, with one exception. The only time polyethylene outgasses when a substance breaks down, or the poisons in the substance or other chemicals in the substance evaporates into the air and you breathe those. Polyethylene does not outgas, with one exception, and that's if you get it in the sunshine. If you get it in the sunshine, it will outgas. That's why the polyethylene breaks down in the sunshine. Many of you may have used polyethylene over, say, a greenhouse, and you'll notice that by the end of the season, the polyethylene has deteriorated, and it's breaking up into small little pieces. It does not deteriorate underground. It does not deteriorate because about the only thing that breaks down polyethylene is ultraviolet light. And of course, underground, you're not going to have that ultraviolet light. In fact, polyethylene lasts so well underground that the environmentalists are quite concerned that the garbage that we're burying in our landfills, in the garbage bags, are going to be there 200 years later for our descendants in primo condition, because the moisture hasn't gotten to it, the bag hasn't broken down. That's a negative aspect of the usage of polyethylene, but you're going to use polyethylene in a positive manner. By no longer having footings and a foundation, you are going to eliminate, I believe, most of the hazard of earthquake. And the quakes are coming. You might well consider going underground in a post-shoring polyethylene home, specifically to deal with earthquakes if you're in an earthquake area. Now why? Why is an underground built with PS superior, we think, in an earthquake? Because all underground structures do better in a quake than above ground structures. The reason for this is, when you build a house like this, here's maybe your earth level here. When you build a house above ground and a quake comes through, what happens is this ground is rippling like this. And this structure above isn't rippling. The structure above is inert. And what happens is you have a shear zone in here where this foundation is moving, yes, and even concrete structures underground will ripple with an earthquake and probably not crumble. But where the structure crumbles is in this shear zone. And when your foundation crumbles, your structure above comes down. By going underground, you immediately eliminate that. And by going underground with a post-shoring polyethylene method, you do even better. Here's why. The Japanese invented the post and beam construction specifically to deal with earthquakes. You've got a land surface like this, and post and beam construction are posts set down in the ground and beams above this and the structure, siding in here, a window. When the quake comes through, all of that is transferred up into the structure above, so that the whole structure moves with the quake. You don't have the shear zones. The whole structure moves. And the Japanese, who have a lot of earthquake problem, found that this method does work. By putting this method underground, you've got the best of both worlds. You've got the flexibility of wood. You've got the whole quake moving through the structure, flowing through the structure, and no shear area at all, no shear zone. So, it's a lot of reason right there for not building a house with a foundation, for eliminating the foundation. Save 15% of the cost. Your pipes will never freeze. You'll wind up with superior flooring. You'll wind up saving flooring costs, because you don't have to build a wooden floor. A wooden floor is costly, friends. You've got to put in studs every 18 inches anyway, usually at least 2 by 6, usually 2 by 8 studs. You've got cross bracing in there. You've got a subflooring, usually building paper on top of that, and you've got your top flooring. That's a lot of cost, and it's a lot of effort to put that down. You can put it on a concrete floor, but if you do that, you're going to be getting varicose veins Housewives hate concrete floors, whether they know it or not. That's why they get varicose veins. That's why they start getting all kinds of problems with their joints and so forth. And a friend of mine who worked at a shop here in town, a butcher shop, and concrete floors, he tried everything. He tried rubber mats, he tried duck boards, he tried special shoes. He finally had to give it up because he still had to walk on concrete too much. And housewives, people who work in factories, salespersons who work in stores with cement floors, almost all of them have trouble because it's unyielding. Same way joggers have trouble when they run on pavement instead of running on trails. Joggers almost always wind up with bad knees, ankles, and so forth. So, we try to talk you into the post-shoring polyethylene method of building. I personally think, and many are beginning to agree with us, that underground housing is the most aesthetically pleasing. Why? Because you can't even see it. Now, true, you're not going to be able to drive up your circular driveway and step out of your car and see a massive house with big pillars and beat your chest and say, this is what I am worth. Instead, if you insist upon driving up to your house, I happen to hike into mine, if you insist on driving up to your house, you're going to see pretty much a natural surface, growing vegetation on your roof, some doors and windows peeking out of the earth, and that's what you're going to see. That, to me, is aesthetically pleasing. Imagine our cities if they were built like that. They'd look like parks. And we'd have the roofs of our houses purifying the air. You also have a minor wildlife refuge up there on your roof. You're going to pay less taxes, these underground houses, because they cost less to build. And also because your tax man is going to think that they won't sell for as much as an above-ground house. Now, this happens to be true in most of the concrete houses that were built in the last, 20 years. In the early 1970s, we had a big run on underground housing in the United States. And they were building concrete structures by the first thought method, which we'll be discussing later, many of which simply can't be sold now. Those people are living in concrete tombs. It's what they look like, it's what they feel like, and nobody wants to buy them now. On the other hand, the one method that is still going, the one method of underground construction that is not only still going, but is picking up enthusiasm, is the post-shoring polyethylene method. It's because it's warm, livable, breathable, wood-paneled homes with an abundance of light, air, and views, which we're going to emphasize in the second tape. Nevertheless, your tax man is going to think that this is worth less, and you're going to pay less taxes on your underground house. When the tax man comes out to assess your place, you say, what? For this hole in the ground? And it works. These places are warm in the winter and cool in the summer, underground housing. Why? Because the earth maintains a steady temperature 8 foot down here, 8 foot down, it maintains a steady temperature, which is your average mean temperature of the year in whatever area that you're in. Up here in North Idaho, that's about 52 degrees. It'll vary somewhat in here a little bit, but the heat that you're putting out in your house will make a warmer area in the winter time. It'll heat that up to probably around 60 degrees. In fact, I can say on an average my house anyway, the earth outside my house, generally year-round, stays about 60 degrees. Now, when it gets up to 100 degrees outside, everybody else is having to cool 40 degrees. Hey, I'm already there. I oftentimes literally have to open my doors and windows in the morning to get in a little warmth, warm it up a little for the day, and then I shut my windows when it gets up higher temperature so that I don't get that heat in. But my place stays nice and cool all summer long. When it gets down to 0 degrees, everybody else is having to heat 72 degrees. I'm having to heat 12 degrees. A little more because I have heat loss from my windows. We'll talk about how to cut the heat loss from your windows too. But for argument's sake, let's just say I'm heating 12 degrees and they're heating 72 degrees, a 60-degree differential. You're saving tremendous amounts on your fuel bills, especially if you use thermal pane windows and so forth. So over the course of say a 20-year span in your house, 21 years like I've been in my house, figure what your average heating and cooling bills are. And figure that when you go underground, you'll cut those at least in half. And then you'll know how much savings you're going to have over that 20-year period. You can have a better view in underground housing. This is one that get a lot of skepticism on. Let's see how a better view is possible. In most instances, in a city, which is where most people are living today, in cities or suburban areas, urban areas, you're building houses that are right next to each other. What is your view from this house, from any other house? Your view is of the house next door. Consequently, most people who live in urban areas keep their blinds drawn. And when I was first going around trying to convince people to go underground in the early 70s, I had a lot of trouble with housewives over this concept. They would say, but I have to have light, air, and views. I have to look out. And you look around their house, and every blind in their house is drawn so that the neighbors can't look in. And when they do draw the blinds open, what is their view? It's of the house next door. Let's take instead an underground development. We're going to build a little sunken patio here, put a structure in, underground structure, have another sunken patio here. Another sunken patio, underground structure, another sunken patio. Now, your windows are in here and here, and they're looking out on your garden area. You don't see the house next door. What you see is your own garden. Little rock garden, whatever you want there. A full patio out here where you can go out, lounge around, whatever. But what you're looking at is your garden area. You're not looking at your neighbor's house. You can leave your blinds open. You can get the light air sunshine, cross ventilation in your house, and you got a view of a controlled environment, a rock garden, Japanese garden, flower garden, whatever you want. Who has the better view then? The people who are underground or the people who are above ground? You can build in a greenhouse in these structures. It's just this simple. Put tempered glass or fiberglass over here. Now the 52 degrees temperature from the earth and the 72 degrees heat loss from your house and the sun shine coming down will in most cases keep this within growing temperature range year-round without any other cost to you. You aren't going to have to heat this. We'll show you a greenhouse perhaps later on, and certainly in tape 3 we'll show you a greenhouse that I built into the side of a hill, earth sheltered. I did not even have the 72 degrees temperature from the house heating this. In fact, I had no heating. I have no heating in this greenhouse other than the earth and the sun. And it takes my tomatoes here in North Idaho. It takes my tomatoes generally into the second week in December, when everybody else's tomatoes in their gardens are lost almost always in September, and if they have above ground unheated greenhouses, generally the first or second week in October. Mine takes my tomatoes clear into December, and it'll take things like kale, Brussels sprouts, some lettuces, Swiss chard, those sort of things, the hardies. It'll take them clear through the winter. It's done it winter after winter for me. That little bit of fiberglass holding in the heat on this greenhouse is not only going to allow you to heat that greenhouse automatically from the earth, the sun, and the heat from your house, but it is also going to hold the heat down over your windows so that there is less heat loss from your house. The house heats the greenhouse heats the house. So one of the few cases I know of having your cake and eating it too. These places are ecologically sound, again, because you're using less energy to heat them, to cool them, because you're using far less building materials. You're using almost no manufactured building materials. And because the earth is a living, growing surface. That living, growing surface also becomes yard space for you. If you're paying $20,000 for a city lot, and your house is taking up half that lot, if you put that house underground, you have doubled your yard space. You've just got yourself a $10,000 bonus in yard. These places are fallout shelters. It's been estimated by reputable authorities, and we'll go into this in tape 3, heavily into tape 3. It's been estimated that with a little care, an underground house can give you a protection factor of 40, which means for every 40 gamma rays that would hit you if you were standing up outside, if you go underground with a little care when you build your underground house, only one of those gamma rays will get through. Only one out of the 40. It's a protection factor of 40. And that's the best that the civil defense, United States Civil Defense, could hope for you in those basement fallout shelters that they were trying to get us all to build in the 1950s. You'll also cut other radiation. And I don't know if you're up on this, but there is all sorts of worry about electromagnetic radiation. It's opposed to, it's called a non-ionizing radiation, electromagnetic. Ionizing radiation is a nuclear type of radiation where actual particles bombard you. The non-ionizing radiation and the particles change the actual cells in you. Non-ionizing radiation is not particle radiation. It's energy, wave energy. And it goes through you. But while it goes through you, it's causing great distress to your system. And if you go underground, you're going to cut out a lot of that for two reasons. First of all, the Earth itself cuts out much of that radiation. And second of all, because much of that radiation is beamed above ground. TV towers, radio towers, and so on and so forth, microwave towers, they're all beamed above ground. And you go underground, you're getting away from that, from the beam, and second of all, you have that mass of Earth to muffle that beam, that radiation. So, if you are concerned about that, as many of us are these days, know that you will be doing better underground. These places are defensible. Where does the Army go? If it wants to defend itself, it goes underground. If it ever comes to that and you feel as though you want to defend yourself, you're better off underground. Concealment. That may be the best defense of all. You build these underground structure back in the woods, and you don't have a big road going into it. When and if this country goes up, as it may, in fact, as it seems to be doing, when and if it goes up, if you are concealed, you can conceal your family, you'll probably get through the worst days. These places are relatively fireproof. Not 100% fireproof because they're built with wood. But they are relatively fireproof for one great big reason. There's only one surface. This is Earth out here. There's only one surface that the air can get to. When you build a frame structure, you have four surfaces. The outer surface, this inner surface, and that surface there that the air can get to. And unless you've got some really good fireproofing in there, this surface will burn against this surface. You know how fast frame structures go up. They go up real fast when they go. I'll admit that I've had a number of fires in my house. I have a stove that for years has been too close to the wall. When I had the old tin stove, before I got my big fancy heavy cast iron stove, steel stove, that tin stove really threw out a lot of heat real quickly. And this wall over here has on occasion singed. But it has never spread. It has only burned where there was direct heat from the stove. It didn't have anything to burn in tandem with. If you take a stick, a burning stick out of a campfire, and you just hold one stick up, you'll notice that that'll go out, burn out pretty fast. But if you hold up 2 or 3 sticks, it'll burn a lot longer because they are burning in tandem, continuing to raise the sticks to the kindling temperature. Once you put out this stove or put a barrier between it, this will put itself out. Okay? It has never spread on me. I've got a sauna. Same problem. Stove is too close to the sauna. I'm so lazy I've never put any kind of metal or asbestos or any kind of fireproofing up there. I don't need to. Okay? The fire never spreads. I did have one very bad night when a kerosene lamp went over in my house. Flaming kerosene fell on the carpet. And I had a wooden table above that. By the time I got to it, the flaming kerosene had set this table on fire. And now I have to tell you, I told you, I hike into my house. By the closest trail, it's about a 10-minute hike into the house. No way a fire department could have got in there. But we don't have a fire department anyway. I didn't have a fire extinguisher in the house. I had just a little water, but I didn't want to throw water on a kerosene fire anyway to spread it. Did I panic? No. What I did was I ran outside, I grabbed a shovel, I pulled back my carpet and the polyethylene on the floor, and I put out my house with my floor. Right. Throwing the earth from the floor on the fire. Put it out. So your house itself is sort of an automatic fire extinguisher. And of course, your roof is not going to burn because it's earthen. Many of the fires that we have out here in the country, in fact, probably 80% of them are caused by wooden stoves. And many times that's caused by the spark from the stove onto, say, the roofing, asphalt roofing or shingle roofing. You have a growing earthen surface up there, and it's not going to catch on fire. I've mentioned that your pipes never freeze underground. I've tried to talk you into the superior flooring, the earth carpet flooring, which is like walking on a golf course green. Really good for your system. It's what you were meant to walk on, is earth. It's what you were designed. Your Creator designed you to walk on earth, not on concrete. Of course, it's much cheaper. Dirt cheap. These places can be built by anyone. There's rarely anybody in my audience who can't build one of these underground structures. They're weatherproof. No matter how high the winds get, it's probably not going to do in your house. It might take off some earth on the house. It might do and blow in a few windows, door, but your structure is going to last. Those of you who know the writings of Ruth Montgomery, you might be aware of the fact that Ruth Montgomery's guides tell her that in the days ahead, after the pole shift, we're going to be having 200-mile-an-hour winds. We're already getting 120-mile-an-hour winds. It's part of our weather pattern these days. But we're going to be having, according to her guides, 200-mile-an-hour winds after the pole shift. And they say that most above-ground structures are going to collapse. You have less maintenance on these underground houses. Hopefully, the second of these of this series, the second tape, we're going to be able to see a little structure I lived in for a year that was on my land, which was the inspiration for going underground, a miserable little shack that I've roofed twice in my total of 24 years on that land. 21 years I've been underground, but 24 years on the land. I've had to roof that twice, and I've never had to re-roof my underground house yet. So there's far less maintenance. And another advantage is these are relatively soundproof, these underground structures, depending again upon the type of windows you use. Malcolm Wells, underground architect in the East, when I visited his office in Cherry Hill, New Jersey, his office was located literally within a beer can throw of, I think it was a 8-lane major New Jersey freeway with trucks rumbling by all the time. And it was quiet in his office. And he told me, he said, "Mike, go into the bathroom and close the door and listen." So I went to the bathroom, I closed the door, and I listened. And I could literally hear my heartbeat. In this day and age, it's a nice advantage. Let's talk a little bit now about the actual construction. It's this simple. Dig a hole. If you have a little money, get a cat to dig that hole or a backhoe. If you don't, dig it by hand. I've dug all my structures on my land by hand. Excellent exercise. After you get the hole in there, you sink posts into the ground. Tables in the book will tell you roughly, will give you a guide. How thick your posts should be, how far, depending upon how far spaced apart they are, and also your girders and beams. Now, I said that we used to treat our posts. We used to use Penta. Penta dissolved in diesel oil, which is what all of our farmers were using for fence posts and for their post and beam barns and so forth that they were building out here. I don't go for that anymore. We're poisoning the earth. It's not a healthy substance to live within. So what I'm doing these days are two things. One is I'm making piers out of concrete, and I use stovepipes, 6-inch or 8-inch stovepipes for a wooden stove. Get them at any hardware store. And instead of putting the pipe all the way together, as I would, clicking it together, as I would were I running smoke through them, I just put them together loosely, and I take some plumber's tape. That's the metal with a lot of little holes in it that you buy, a metal strip, a lot of little holes in it that you buy at a hardware store. And I put that around the pipe in 3 places. It's a 2-foot length of stovepipe. Put it around the pipe in 3 places, and I run a bolt and nut through there. Put it together loosely. I sink that down on the ground a few inches. Here's the top looking down. Then I lay usually some chicken wire or sheep wire or something of the sort around, roughly around the outer edge, not touching the outer edge, but close to it. Make a loop of it, set that in a cylinder of it, and set it down in. And then I put a rebar down in here. Run this rebar, 1/2-inch rebar. Run it down like that, and run it about 4 to 6 inches above the top of the stovepipe. Then I mix up some ready mix concrete in my wheelbarrow. I shovel that in, and I pound the heck out of this with a hammer or a board or something. Pound the heck out of the stovepipe to get the air bubbles up. And I leave this for 12 hours, 24 hours. I take the plumber's tape off, pull the stovepipe off, and I'm ready to use it again. I've got a pier now, and I'm ready to pour again in the stovepipe. I might add, I must add, that I grease the stovepipe first. I oil it first. And you can use almost any kind of oil. What I use is old motor oil when I change the oil on my car. I save that oil, and I oil the stovepipe with that. This is a method. It's a good method. It's a particularly good method if you're in an area that the water table might come up on you periodically, or you might have a lot of moisture traveling down through that. What you do is when you set your post down on this, you drill a hole in the post, and you set the post then down on over the pier. The problem with this is lateral thrust again, our old enemy lateral thrust. When you backfill in here, you may, we were predicting that this was going to happen from the beginning. Unless you take some precautions, you may cause this to hinge. That is to say, the pressure pushing in here is going to push this pier in this way and this post in this way. So now they're going to be at this angle. Ways of getting around this, of course, are to join this post to this post with shoring, siding or something, or to use this pier system out in the middle of the room. Okay? But you're probably going to have to do something to keep that from pushing in. Just be advised, it may hinge on you. My preferred system now, the one that I am building with most often, with the exception of when I go outside, when it's not protected, is to char the post first where it goes into the ground. Char it over a campfire. Char it up maybe a foot higher than what's going to go into the ground. If you go 2 foot in the ground, maybe go 2 foot 6 inches or 3 foot and char it. Char maybe a 1/4 inch of char there. And your post is going to check on you. Checking is when it cracks, either with heat or if it dries too rapidly. It'll check. And that won't char in your campfire. That'll be raw. Okay? What I do then is after I pull out of the campfire, I take a little blowtorch, a little butane torch, and I just run that up and down the check so that it all chars. Now, what the charring does, this is an old farmer's technique. In the country, farmers, before they were using the poison, were charring their posts. They found that it lasts at least 50% longer when they sink say a fence post into the ground. And then what they would do is they would char the top and turn it over after it rotted out, after maybe 15 years up in wet country as we're in now, in our part of the country. The charring, first of all, hardens the wood. Indians knew this. They always hardened their arrowheads and so forth by scorching the wood. People who make bowls and so forth out of wood always char it, heat temper it. So it hardens it. Second of all, it makes that charcoal outer layer, and most critters simply don't want to eat charcoal, whether they be microbes or what. Most critters don't want to eat charcoal. And the third thing that happens is it makes its own natural creosote. Creosote is the end result of incomplete combustion of wood. And of course, that's what the char is. So those three factors help. Then what we do is we take that part of the post, before we set it in the ground, we wrap it in 4 or 5 or 6, if you want, garbage bags. Make sure you don't get the biodegradable kind of garbage bag. The garbage bag is polyethylene. It's 1.4, generally 1.2 or 1.4 mil polyethylene. And we put layer after layer on that, and we tape it up tight. Then we set our post in the ground. If you're in rocky ground, put a little section of newspaper out around that and tape it so that the rock and so forth, when you backfill, doesn't puncture the polyethylene. I think that this system is going to take our post probably 100 years. There's some question of what happens when you have the weight of the house on top of these posts in the garbage bags. Isn't that going to poke through the garbage bag? Well, I knew intuitively that it wasn't, but I had a client in South Carolina once, North Carolina, who wanted a demonstration. So we cut off a 4-foot section of post. We wrapped them in 4 garbage bags, set that down on the ground, we tamped it, and we brought in a backhoe, a large backhoe. It was on the job. And the operator put the loader, that big bucket, the big bucket, on top of that post, and then he lifted up the backhoe, one half of that front part of the backhoe, all on the weight of that one post. We left it there for 15 minutes. Then we dropped the hoe, dug up the post again, and both the client and the backhoe operator's jaws dropped because only the front garbage bag had punctured. Only 1 out of 4 had punctured only in 1 or 2 places. After you prepare your posts, you sink them into the ground. Line them up. Put in one post here and one over in the other corner. Run a string across and a line level on it. And so you'll know the level of your posts. If they're uneven height, which they probably will be, then after you run that line level over, then you can trim them with your chainsaw. And that line level will also line up all your other posts in here. Generally, I like to work with posts 6 to 8 feet apart. So on a, if they're 6 feet apart on a 30-foot room or house, you're going to have 6 posts in any one wall. You'll want to line those up with a string. After you get that, then you put a big girder all the way across. If they're too big for you to handle, you can cut it in the middle and splice it through. Splice them. We put the girder in, we drill a hole down through the girder and a few inches into the post itself, and we drive a rebar in through there. So it's flush, or even a little lower here. Then we put our roof beams in here. Now and then our roofing material, usually building paper, and then a layer of polyethylene. 6 mil will do you, 10 mil if you're rich. 4 inches of earth, another layer of polyethylene. I have to point out that you're seeing this from the end section. We always build with a good pitch on our roofs. Always. Flat roofs leak. The pitch I like best of all is a pitch of 1 3, which is to say, for every 3 foot of floor area, there's fall of 1 foot here. It's a pitch of 1 3. A carpenter would call that 4 and 12. I'll sometimes go as low as 1 and 5. I'll sometimes go as high as 1 and 2, but that's about the range that I work with. 1 and 3 is my favorite pitch. You go 1 and 2, you start having some difficulties keeping the earth on the roof. You go 1 and 5, you're beginning to get into the possible leakage zone. Once you get this structure, you don't have to put on the roof right away if you don't want to, but I like to put on the roof pretty quick and get some polyethylene down there so you can work underneath without being in mud. After you get this structure on, then the next step is to lay out some polyethylene. And I anchor the polyethylene on the first board that goes in. Let's say it's a 6-inch board. I generally go down about 2 inches into the earth. And I put the polyethylene under that, and then I bring it up in a big bunch, and I curl it up. I usually come up a couple of boards here and a couple of boards at the same time on the other side. And you can either go all the way up the wall now, or you can start backfilling right away. Lots of times when I'm digging by hand, I leave earth out in here, out in the center. And I'm still digging. And I dig, and I throw that over there, and one shovelful excavates the house and backfills it at the same time. If you're working with a backhoe, you'll have a mound of earth out here, and you can just throw it in by hand, or you can gently put it in with a backhoe. We'll talk about backfill in a moment. But anyway, you put in your shoring here, all the way up, and then you stretch your polyethylene up and bring it out partway over the roof. And you do the same thing on this side. Stretch it up, bring it partway over the roof. At no time do you tack the polyethylene up here. Once you get it brought out, you can tack it up here if you want to hold it in place. But you do not puncture the polyethylene in the sides. For the obvious reasons, it's going to bring in moisture if you do. When you backfill, you have to take a lot of care. You have to know several things. First of all, you don't want to puncture the polyethylene by throwing rocks and so forth down on top of it. One way of getting around that is as you go up, use cardboard to protect the polyethylene. Nestle it a little bit in the earth here, put a couple of shovelfuls in. And the cardboard I'm talking about is plain old cardboard from your grocery store. Just go to your grocery store, get boxes for a couple of weeks, and flatten them out. Rip them apart and flatten them out. You can use that. If you're in a heavy rock area, or if you're going to be backfilling with a backhoe, or, God help us, a cat, if you're going to do that, put your cardboard there, and then also some light plywood. And the cardboard will stay nestled against the polyethylene, but the plywood you can keep raising all the time, so that the force of that material coming down is absorbed by the plywood. And then the cardboard, when you move that plywood, the cardboard will still protect the polyethylene, and you leave the cardboard there. It'll rot out eventually, but by that time the rocks and that will have gentled up against the polyethylene. Now the second thing you have to know on the backfill is you don't bring in a cat and shove the earth up against the house. If you shove the earth up against the house, the same thing is going to happen on this house that would happen on your frame house. Your whole house is going to go like that. I prefer to backfill by hand myself, at least in the early stages. And I'll backfill a foot or two here, and I'll tamp it well with a 2x4 turned upside down or on its edge. I'll tamp it with a 2x4 by foot tamp. And I'll tamp it well for a foot or two over here, and then I'll go over on this side and do a foot or two over here. And then I'll go back again, do another foot or two, again another foot or two, all the way up, balancing it all the way up. If you don't, if you just backfill this one side and tamp it, again, the whole structure is going to go. I can't emphasize that too much. I've had people build structures of this method and sometimes you'll build a structure that will have, let's say you're building on a flat land. You build with a shed roof. I prefer a shed roof. This is a shed roof. This is a gabled or a peaked roof. Okay. I prefer a shed roof for a number of reasons. But let's say you're building on flat land, and here is the regular earth level here. And you've maybe excavated out here a little patio out here. And maybe most of this side is solid earth. You'll have a gable or something in there, but most of this is solid earth. Plus the weight of the earth on top. And they'll maybe backfill this first, forgetting to backfill this in here, and the whole structure will go forward. Or sometimes they'll backfill equally, and it still shifts a little because there is less resistance over here than there is here. There's more pressure from this side than on this side. Well, what you have to do then, friends, is you have to put in some diagonal braces, like that, okay? Between your posts in this house, you'll have to put in some diagonal braces. But I've had a number of people come up to me and say, Joe, build a house like yours, by your method. And the whole place went like that. And he says, your method is a failure. It's not a failure. Joe's engineering was a failure. or Joe's backfilling was a failure. This can be overcome. It should be overcome. Many of my houses are this way, and they don't go forward. A little plug here for tamping well. If you don't tamp well, say around your posts and so forth in the house, they're going to sink. It's going to settle. The earth is going to settle there, and you're going to have a little dip in your carpet. That'll be true also where you have an elevation change in the house, where this is solid earth in here, and you drop down to an area there, and you've got a retaining wall here. If you don't backfill well in this area here, you're going to have a little dip in that carpet. So tamp well. By tamping well, I mean put in 6 inches, 8 inches of earth, and then tamp with a 2x4 or with a shovel handle until that is solid. All right, let's show you one more thing before we go to the slideshow here. I'm going to show you a mistake I made. And I've made a lot of mistakes. And we're going to see in the slideshow mistakes other people have made. We're pointing these out not because we're dumb klutzes, but so you don't make the same mistakes, okay? I wish I had had this course myself when I first started. It would have been immeasurably easier. The first engineering mistake I made was, and we'll see this in the first slide, see me doing this, was I had the excavation and I was putting in a post and a girder. And for reasons it's too difficult for me to explain right now, I notched the post like this into my girder. It's a notch like this into the girder. And then I backfilled. And there was a slight hillside, and hillsides moved, called hillside creep. Hillsides move, exert a lot of pressure, and what happened was these posts began to push in up here. What I should have done, and what I did, of course, after I discovered this mistake, was notch the posts from then on so that they were like this. So that the pressure of the earth against the shoring, the pressure of the earth transfers to the shoring, which transfers to the post, which transfers to the girder, which transfers to the beam going across the house, to the other girder over here, to the post over here, to the shoring here, and to the earth here. Well, the pressure is against the earth there. I think of this as bone support. Like ankle bone connected to the shin bone connected to the knee bone, etc. That's what keeps you up, is these bones are supporting each other. If your thigh bone was out back here and not directly over your knee bone and your shin bone, you wouldn't be walking for very long. This method here, this bone support method, actually uses the pressure of the earth as a component of the house. The pressure here being transferred all the way across to the counter pressure here becomes a structural plus to the house. There ain't much going to move this house. Not even an earthquake. It'll move it, it'll shift it a little bit. It'll bend it a little bit. But it's not going to push it around. And nothing else. And the high winds, nothing else is going to move this house. It's as solid as the earth itself. So know that the earth is your friend on underground construction, if you deal properly, if you have the bone support so that all the components are notched and pinned together so that the pressure from here is transferred across to the counter pressure here. One more thing I have to put in here about insulation. There was a big deal about insulation in the early 70s, and this is another place that I was fighting with what I call the concrete terrorists, the guys who were building underground with concrete. They were going and they were insulating the whole thing, all around. Floors, roof, walls, styrofoam, 4 inches of styrofoam, because they said the heat can bleed out into the earth. Well, it can. But it bleeds out a couple of feet and maintains passive heat storage out there. Okay? If you insulate, you're insulating away from the 52 degrees that is going to come into your house when you're away or when your stove is down at night. Your house is rarely going to go below 52 degrees, okay? Because 52 degrees out here and 60 degrees here. Furthermore, if you insulate, you're insulating away from the cooling effect in the summertime. In the summertime, it is drawing the heat off when you want it to. It's drawing that 100 degrees out. So nowadays, they've modified that, and they're insulating from the 3 foot up and over the roof. I don't even do that. What I am doing these days is running 2 layers of lumber on my roof, 2 layers of 2-inch lumber on the roof. So I have about 2-inch lumber today is 1.5 inches, actually. A 2x4 is 1.5 inches by 3.5 inches, I think. That's enough insulation for me. And then you have the earth on top of that, 18 inches of earth on top of that. Let's go to the slides now. This is the original $50 underground house. And you can see I'm making the mistake I told you about. I'm notching these posts on the inside of the girder. And eventually the posts that were put in to these girders up here pushed in, as we'll see in the slides in a moment. Nevertheless, the house was a success. This is what the house usually looked like, the original $50 underground house. I had a straw floor on this house, by the way, and which was actually great flooring, except once in a while you did have a little forest fire on your floor and you have to leap out of bed and build some fire lines. And if you ever lost a contact lens in that floor, you were done. But it was a beautiful floor otherwise. It smelled good. It was kind of fun to sit on. My dog loved it. When I put carpeting in the house later on, the dog hated the carpeting. For one reason, because I did not use wool carpeting or cotton carpeting. I used a store-bought, a manufactured artificial carpeting. And the problem with the artificial carpeting is that it's glued to the base, to the subcarpet, and the glue is terrible poison, and it outgasses. And my dog was laying on that and sniffing it. He did not like that. This is what the place looked like. It was a little cleaner. That was the door going out in the uphill patio. The original doorway into that house was in the uphill patio. It was nice looking when it was cleaned up. This is looking down through the uphill patio, and in the next tape we'll go into this again and again, the advantages of the uphill patio on an underground house. The uphill patio again. And this is what the underground house looked like, the original $50 job. Here is the uphill patio. This is what I call the fire windows out here. They used to have campfires out there until I discovered very quickly that all the smoke was drawing up through the house. So I never used that for campfires anymore. Instead, I put barbecue windows in here. We'll see that in a minute. You can stand inside and cook outside, and all your smoke and heat escapes. This was the roof of the house here. That's the original $50 underground house, built in '71 and still there. This was the posts beginning to push in here. And this was some propping, some temporary posts that I put in here to keep the place from collapsing while these posts pushed in. I had a choice then. Do I just repair this wall, do it correctly, or dig the whole thing out and put in another room altogether? The polyethylene here, I use clear polyethylene on this. Question, do you use clear polyethylene or black polyethylene? I don't really know what's the better. Black polyethylene lasts better when the sun hits it. The clear polyethylene, on the other hand, is supposed to be made of purer stuff or something, I don't know. Either will work well underground. This was only 4 mil, this polyethylene. I usually use 6 mil today, now that I'm a little richer. But even that 4 mil did not tear or puncture any place in the 4 years that it was used there, and it was as pliant as the day I put it in. There was a gopher. You could see a gopher when we dug this out. Gopher had come up, touched that polyethylene, traversed it, and split, and never punctured it in any way. There wasn't a tree root that went through it. There wasn't any kind of puncture in that polyethylene at all. That's Chris Royer up on the roof. He was a volunteer for the summer, and he's now an architect up in Boston, and he's the guy that did the illustrations on the $50 and Up Underground House book. Now these posts here, there's another volunteer, this isn't Chris. These posts here are notched the proper way now. The girder is going to go here, and the pressure from the earth is going to push against those posts, which will push against the girder. All dug by hand. Chris is setting a post, and he's tamping it with a shovel handle. Putting in a new girder there. We removed one girder, and we're putting in another one now, a much longer one, because this section in here is going to be an offset wall. And we'll talk about that on the next tape, what an offset room is. Nowadays, we don't use nails or spikes. We drill a hole through this and down a few inches into that, and then we drive a rebar down through, about 6-8 inches into this post. These boards here are not the roofing. We're going to have beams come across like this here. We have the beams come across, then we lay down our roofing. These boards were just to facilitate working on top of the place. Posts, girders, beams going across. We'll have shoring out here and polyethylene. This area right in here is going to be what we call the Royer Foyer, named after Chris, and we'll explain that in the second tape. These are the mill ends. It's imperfect lumber cut up by the mills, thrown away. We got them for free. We had to use 2-foot spans. I think on this one we actually went 3-foot-6 spans between the posts, used 4-foot mill ends. In the original $50 underground house, we used just 2-foot mill ends. Then we're laying down building paper. We're sweeping it. This is Ricky Hudson, a neighbor. He's a volunteer. We're sweeping it off so that there's no lumps in it to work through the building paper and through the polyethylene. Polyethylene laying over a lump will do what's called a creep. It'll thin out and eventually may puncture through. So we have as smooth a surface as we can get. The building paper I'm still leery of. I think it outgasses. I'm not crazy about building paper. It may also be that the building paper dissolves the polyethylene. I haven't researched that one yet. I hope it doesn't. That's one of the reasons why we put down 2 layers of polyethylene. Ricky is rolling out the first layer of polyethylene now. You don't want to do this in a wind, let me tell you. Do this in a wind, and it's going to be wrapped around the nearest tree. I try to use a solid sheet all the way across the structure. When we went from one room to another, then we overlapped about 3 foot on either side. On this shot here, he's beginning to put some of the polyethylene, some of the earth. We have polyethylene and then 4 inches of earth, and then the second layer of polyethylene, and then 18 inches of earth up on that. The reason for that is if the top layer punctures, there's 4 inches of earth that the water can disperse and move off downhill in, and it won't gang up on any puncture that's in the lower polyethylene. Here we're smoothing out a floor. And to do, say, an 8 by 12 foot floor in this kind of soil, it might take me a full day to smooth that out. I go over it and over it again with this 2 by 6, and where it scrapes off, I take the scrapings and I put it in the low place, and I turn this 2 by 4 up on end and tamp. And then I scrape again until it's as smooth as concrete finished by a professional finisher. And then I lay down my polyethylene, and then I roll out my carpeting, and it's just a marvelous floor. This is the beginning of the Royer Foyer out here, which is a pie-shaped excavation into the hillside, which allows me a doorway, and we'll see in a moment. And this is an ant hill out here, by the way. There's carpenter ants, and yes, they are a problem in a wooden underground structure, and the way you deal with those is if you don't want to use poison, which I don't even want to poison the anthill because they're living creatures too. What I do instead is I dust the area where I know they're coming in at with boric acid, the powder form, and that repels them. Cayenne pepper is also supposed to repel them, and originally I was using stuff you get from the gardens, bone meal that you get from a garden shop. That's really smelly stuff and doesn't work as well. Boric acid works really nicely. And boric acid is benign to you. After all, that's what you wash your eyes out with, which means you're swallowing it too. You're getting it down through the tear ducts. So it's pretty benign to you, but the ants just hate it. This is a Royer Foyer. This is the actual hillside, the pitch of the hillside, and this is the roof over here. Okay, and the hillside comes down here. We've made a pie-shaped excavation into that. And the earth from the excavation of the house, we brought out here, out into the foreground where we're standing, and we filled the hillside there. So we have a level area. And that means that when I'm cutting my firewood and so forth out here, when I walk into the house, I don't have to climb up or down. I'm walking directly into an underground house, which is actually 7 feet deep or 8 feet deep at this point. And I'm not climbing up or down at all. I'm walking in. This is a pack in the foreground here, and elk. We were just coming back from tree planting, commercial tree planting, and we found some elk antlers, elk racks. This is what the house looks like. I've varnished the posts and beams, and it's dark in here because of a very dark carpet. A dark blue carpet doesn't show up well. I could have lightened the house considerably if I put in a light yellow or orange carpet or something of the sort, but since I don't have commercial electricity over there, just solar electricity, I wanted a dark carpet. I also like dark carpet anyway because it's meditative. That's Chris and Sarah, his wife. And right over the top of Chris's head is the barbecue windows. And Sarah now is leaning out the barbecue windows and she's cooking. And all the heat and smoke escapes. And she's inside. She can cook inside out of the rain. And this is the study area. It's where I do my writing. You see Sarah now outside the barbecue windows cooking. She's standing inside and leaning outside, and you're seeing this through the offset wall. That's all windows in this particular house. And down over here, you see the original fire window. This is the offset wall of windows here. And just as a note, this is you see the picture of a bear that was shot in the book, and this is the window I shot him out of. And this is my uphill patio here. He was coming down into the patio and wouldn't leave. This is a crew of 2 volunteers from Princeton and a professional carpenter, Bob Clark, and they're pulling in girders for a house we call the crew house. Here I'm using a chainsaw and what's known as an Alaskan mill to flatten off one side of a post or a beam there. Mr. Princeton here is setting several layers of polyethylene down over a concrete pier that we have sunk in the ground. And Tavia, our beautiful crew cook here, is drilling a hole in the post, and we're going to set that post down on top of the pier. This is day 2 in the construction. So how far we got. Day 1 was not doing the digging. Day 1 was setting the post. So it was dug all by hand, and it was dug over a period of years. I used to allow volunteers out the place, and people who want to come out and learn underground housing, and I'd find out how sincere they were in this desire by putting a shovel in their hands. And yes, I dug a lot of that myself. Since they're set up on piers, we had to use a lot of braces and supports. It's a lot easier if you use the charring and garbage bag method and sink your posts a couple of feet. They don't wobble near as much during construction. This was day 4. And this was day 6. The crew is looking lecherously after poor innocent Tavia here after 6 days in the woods with her. We're wrestling girders into place now. These are heavy. These are heavy guys. Took the full crew to put those in there. What you do is you build shoring, scaffolding along here. You don't see it in here. You see some of the scaffolding there. And then you can put planks across it, and you can work on the, you see he's up on the scaffold. Well, he's on a ladder there. But here's some of the scaffolding over here. You run planks across that, and then you can work with ease on the roof. This is a gable. What we always do is we drain our roof down onto solid earth. There will be solid earth out here on either side of this gable, and the gable drains it off to the side, so it allows us a wall of windows and doorways in here. But otherwise, we always drain our structure onto solid earth. And this is, we'll see with the scale models tomorrow, this is what we call a Hollywood wing, and it's a way of running the moisture down off the earth, deflecting it by the Hollywood wing, and then running it onto solid earth out here. And this will all be windows in here. And these are all windows in here, of course. Hollywood wing is a way of opening up a whole corner of the house to light and air, and still working with your drainage. We emphasize in this course again and again that drainage is your first and foremost problem on underground housing. Solve the drainage first, and then go for your light, air, and views. And this house here has a solid wall, or will have when it's finished, a solid wall of windows on the uphill side and a solid wall of windows on the downhill side, and yet we're running the drainage off onto solid earth, and we'll explain more on the second tape how this is done. You're looking now through you're looking from the Hollywood wing through a lateral window well, and then through the opening made by the gable. This is the inside of the house. It doesn't look much more complete than that right now. It isn't much more complete than that, but we're looking out through the gable now. Here. This is a little sleeper house, we call it. And this house is actually above ground. And what we've done is we bermed earth up around it like this. This is about waist high here. in the house. We bermed earth up around it and then bermed earth over the back. And so this is an earth-sheltered house, not technically underground. This is the type of house where you have to put in diagonal braces in the place. And we've got a couple in there to keep the whole place from shifting forward like that. And this is what we call the garden house because it's over near my garden on the flat part of my land. And this house has a built-in greenhouse here, and then the house itself, and then a root cellar out behind it. It's almost a complete life support system in that little place there. It's not pretty. We've got to paint. These are all used windows. We've got to paint these windows, the frames, all the same color, and shingle it here. And when that's done, it'll be pretty. Same house. And the greenhouse, we flop this back and latch it up here, and we've got a door over here with a window in it, a screened window, and that's enough ventilation even in 80 and 100 degree days to air that out. But always put your ventilation, your vent, and a greenhouse at the highest point. Don't, for example, try to open this window here and another window over there at the same elevation and expect that greenhouse to air. It won't. Put the ventilation at the highest point, and it'll draw out. Interior shot of that little house. Not so bad looking at places. That's looking out into the greenhouse. And this is another underground structure. This structure made the cover of Earth Shelter Living magazine. He built this whole structure, whole house. I forget how many rooms, 5 or 6 rooms, for $2,000. And Earth Shelter Living magazine called this building method by far the best low-cost underground building method they had ever seen. He's got a gable here. This room here, we didn't always agree on. It's nice and light and airy, but he's got moisture dripping off, and it's almost a flat roof, and it's likely to leak. There was a better way of doing that. But aside from that, it's kind of a nice house. And you certainly can't beat the price. That's part of the living room. It's all natural light in there. Look at how it beams into that living room back of there. This was a structure that we designed and built part for a client. It was in very soft sand, and the client was worried about the whole house sinking down in the ground and asked us to put rocks underneath the posts. So we complied. Those are the rocks coming in. You see here we have charred the posts, and we're wrapping them in garbage bags now, setting them into the ground. This is a section of roof that's going to be higher than another section. That's called a clear story, and we'll see that tomorrow. This is the building of the clear story. Here's the clear story here. It allows you to put some windows in here. And here's a gable on the back side that'll have windows in it. All the rest of this on the back side, this is the north side, will be covered with earth, and the whole roof is covered with earth. But wait till you see the windows that we got around the front. Here, I'm working like crazy, trying to keep ahead of the carpenter, trying to figure out where I'm putting these windows in. I'm using all used windows in this structure. And I buy more windows than I need in the house. And what I do then is I measure every window, and I and I draw out a scale model of it, and I draw out the wooden lattices, whatever those are called, that hold the panes in place, so I know the pattern of the window. And then I lay out a big piece of cardboard, and I draw out the silhouette of the area that has to be glazed, the area that has to have the windows in there. And then I spend a good deal of time working on the pattern, shuffling these little figurines of the windows around, trying to get a pattern on these used windows. And you have three textures that you're working with here. One is the lumber that frames the window. The second is the window itself and its inner pattern. And then the third is the fiberglass that you put in around here. This doesn't look pretty yet, but it'll look a little more pretty later on. You'll begin to see a pattern emerge here pretty quick. This is the kitchen area in this house. This entire house cost $8,000. It was half professionally built, half owner built. Earth carpet floor. Is that enough light in there for you? Huh? Think it's going to be dark, damp? Closed-in feeling? No way, man. Now you begin to see some of the pattern here. We're working with three textures again. One is the lumber around the windows, the window itself and its interior pattern, and then I use, quote, clear fiberglass, just old Sears fiberglass, on the areas that I don't have glazing, other glazing for, window glazing for. And that lets in, by the way, some ultraviolet light. You do want some ultraviolet light in your house. Normal window glass knocks out 90% of your ultraviolet light. And ultraviolet light is beneficial. Too much of it is, of course, hazardous, but you're not going to have much to worry about in a house. You do want some ultraviolet light in it. It's one of the most natural, it's one of the most beneficial of all the sun's rays, again, if you don't get too much. It's like water. You can drown in water, but you certainly need water, okay? And the fiberglass will let in 90% of the ultraviolet light, which gives you a little more natural balance in your house. Is this client pleased with his house? Yeah. Okay, this is the kid's bedroom. There's a loft up here, and we'll talk about that tomorrow too. On a shed roof, you have oftentimes a great expanse of windows here, and one of the things you do with that is you put in a loft to utilize that space better. Now you're looking into the kid's bedroom from the living room. This is the master bedroom, and now look at this pattern of windows here. The fiberglass steps down from left to right. The windows step down from left to right, and they're all counterbalanced by this great big window out here. I think that's attractive. That whole wall, all those windows, and all the lumber in that wall probably cost less than $70. If you buy windows new today, one window like this probably cost you more than $70. Okay? We used windows, bought them at Goodwill, bought them at St. Vincent de Paul, bought them at salvaged yards, and made a tremendous savings on this. This is a waterbed, by the way. This is south facing. In the daytime, he whips off the covers here. The dark waterbed absorbs the heat of the sun and becomes a passive solar collector. And then at night, it's like sleeping in the womb. This is the only place on this house, this wooden surface here, that I failed to get windows. One of my principles of design is that everything exposed to the earth, to the air, should be in windows or doors, and preferably glass door. And everything else should be covered. You can't always get that, but on this entire house, this is the only area that I was unable to get windows. I could have put windows in there, but such a thing as overdoing it. Now look at that. Look at those windows. Dark, damp, dank? No way, man. Light and airy. Beautiful view. Everything else on that house is earth covered, except the gable over on the other side. This is a 5,000 square foot, 8-bedroom underground house. I think they figured the total cost of this house was $20,000. I figured out one time how much it would be if they built at the standard building costs, and if they had to pay interest on a bank loan and so on and so forth. It came out to roughly around $500,000 if they had built by normal means and normal financing, and if they had built in an above-ground structure. Unfortunately, these people went to a certified bona fide grade A, genuine, diplomaed university architect who gave them a flat roof. And flat roofs leak. These roofs leak. No laughing matter when you're in an underground house, because you have to pull off 18 inches of earth even to get down to try to look for the leak. Put a good pitch on your roof. 1 in 3 is a nice pitch. Despite that, it's a lovely house. This is a kitchen area, nice detailed kitchen area. The craftsmanship, the workmanship on this house was just superb. It was owner built, and they just did a really superb job. This is an underground house that was being built in Wisconsin. He's building this, incidentally, out of metal beams, because he had access to the beams because he was a welder. And he was putting in a gable in here, but a flat gable, not a peaked gable, not pointed. And what's the problem with that is, well, the problem, of course, is that the water, see, the back side of this is going to be window area, and then you have a roof in here. And the problem, of course, is that your moisture here is running back onto your roof, and the moisture coming down the roof is ganging up on this section there, and it was predicted to leak, and of course it did leak. Right through there. We'll show you at the next tape how to build a gable that works. This here is a structure that was being built in Holland, underground, post-shoring polyethylene, by the magazine Die 12 Ambachten, which incidentally sponsored a tour, took me to Europe, 5 countries in Europe, and we were able to cover the cost of the tour with the lecture fees. In Holland, the building codes are so bad, so tough, that they fly over Holland periodically, all parts of Holland, and take photos. And they compare those photos with the photos taken 6 months ago, see who's been building any structure that didn't pass the code, that wasn't built by the code. And the way they got around that, they didn't even want to try to, in Holland, to try to get a permit to build underground or earth sheltered. So they just disguised it immediately, right away, with turf on the roof, so it didn't show up in the photographs. And to my knowledge, the structure is still standing. I suspect that the authorities probably know about this because he's written about it in his magazine, but they're just turning their backs on it. Now, this is another underground structure in Holland. And this one, again, was built without benefit of official sanction. And one day, this is the lady friend of the owner. One day, the building inspectors came out, 2 of them, and said, "Hans, we understand that you have been building here without the permit. We want to look around and find out what you have been building." And Hans said, "Well," he said, "all right." He said, "Listen," he said, "I'm working in my garden. You just go ahead. Well, I don't have time to show you around. You just walk around and see whatever you can find. And so they walked around, and they walked an entire circle around this house and didn't see the house. They weren't expecting an underground structure. They were looking up. It was invisible to them. They didn't see that. Camouflage. You could hide those windows too if you had to. This is the interior of the house. I asked them what this structure here was. And of course that's a scale model of a windmill. This is an underground sauna that we built on my land in Idaho. You'll notice the opening here, that's for the stovepipe. Stovepipe comes up, it's all covered polyethylene earth, and when it rains, the moisture comes down and goes through that hole in the stovepipe, hits the stove, turns into steam, and automatically humidifies my sauna. Obviously a stroke of design genius. Actually, it was a mistake. Don't ever put a hole in the roof of your structure. If you want to run a stovepipe or anything else out, run it out the side or out the top, the side and then up. But do not run it out through there. I don't care what you got. You're never going to seal that. It's always going to leak on you. Keep that a solid sheet of polyethylene down the structure. There you see the stovepipe coming up now. Putting the polyethylene on now. Ah, yeah, it works. This is a underground library built at the University of Illinois, which I show you to point out some mistakes. This out here in front is America's oldest experimental corn patch, and they didn't want to shade that corn patch with these 3- and 4-story buildings, so they went underground. This is the entrance to the library here, another entrance over here. You're at the entrance now, looking out across. The roof, which you will notice is flat, and what we call an atrium here. This is the view out any window in the atrium is of the other windows. It's one of the reasons why we don't use the atrium. And we will never, ever put a flat roof on an underground structure. That at that time when they built this was in the late 60s. That library cost, I think, $900,000, and they immediately, within the next year, spent another $200,000 trying to waterproof the roof, which they never succeeded at as far as I know. The roof leaks, all flat roofs leak. In my hometown here in Idaho, the library leaks, the jail leaks, the part of the new high school leaked. Almost every building downtown leaks because they have flat roofs. And they get the roofers up there year after year putting tar on them, and they say, hey, these roofers are really lousy roofers. They never stop the leak. It wasn't the roofers that are lousy, it was the architect that's lousy. Any guy who puts a flat roof on a structure is just defying gravity. And if you defy gravity, you are going to have an enemy for the entire length of your time in that structure. If you put a pitch on the roof, gravity is working with you, and you will have a friend for your entire time in that structure. And believe it or not, I think it was old Frank Lloyd Wright who was responsible for talking us into flat roofs. This is an underground structure in California, and the guy here is a tenant living in this underground structure. He loved this house, except for one thing. This is what we call a first thought house, which we'll explain in the next tape. It's a house that backs up into the hillside, has windows only on the downhill side, and a flat roof or a roof that drains back into the hillside. And you have all the moisture coming down from the hillside and all the moisture on the roof ganging up against your back wall. Well, when it gangs up against your back wall, it's going to leak, the same way flat roofs leak. And even though it was, I think, a concrete back wall back there on the backside, it leaked so bad, and with a concrete floor, it leaked so bad in the rainy period that there was a constant flow of water across his floor going out the front door, and he had to put on galoshes in his bedroom to get into the bathroom. And he was asking his landlord to put in duck boards so he could walk dry-footed to the bathroom. First thought houses don't work very well either. Okay, well, we've seen slides now of successful and unsuccessful underground structures. The successful ones were built with a PSP underground system. There are some successful concrete ones too, but not many. As I say, we're not building many of those these days. We are building a great many post-shoring polyethylene ones. We're going to go into the next tape.